Assalamualaikum. Welcome to our data structure lab presentation for CSE'24 I am Irfan, registration number 2024331038, and I will be opening our group presentation today on a topic that sits at the heart of modern distributed computing, that is CRDT, which stands for Conflict Free Replicated Data Type. Before I begin, let me quickly walk you through how our presentation is structured. I will cover the introduction, the architectural shift that made CRDTs necessary, and the concept of eventual consistency. Then, Ruhani will explain the exact problems concurrent editing creates and the historical trade-offs. Prantik will walk us through how CRDT works mathematically under the hood. Noor will present the pseudocode, and finally Shahryar will show how the powers real-world applications like Notion and Excalibur. Alright, let's get into it. The shift to distributed architecture. To understand CRDT, we first need to understand the evolution of the world it was built for. 10 or 15 years ago, most applications ran on a centralized architecture. If you wanted to read or write data, your device talked to one central server. It was simple, and the data was always consistent. But today, the apps we use every single day, like Google Docs, Figma, Notion, operate on a massive global scale. Modern users expect zero latency. To provide that seamless experience, systems no longer rely on one central database. Instead, they replicate data across multiple servers around the world, and even directly on the user's local device. The gap theorem challenge. Replicating data introduces a massive computer science problem. In distributed systems, there is a fundamental principle called gap theorem. It states that a distributed data store can only guarantee two out of three things at the same time: consistency, availability, and partition tolerance. Because modern networks will always drop pockets or disconnect, which means we must have a partition tolerance. Collaborative apps are forced to choose between being strongly consistent or being available. If an app chooses strong consistency, it has to log the document every time someone taps a letter, forcing everyone else to wait for a central server to approve the edit. That completely ruins the real-time user experience. So modern apps choose availability. They let you type instantly without waiting for the server. But that means different replicas of the data, like my screen here in Dhaka and my teammate's screen in London, temporarily fall out of sync. We are both making edits to different versions of the same file. The scaling crisis and the discovery. This wasn't just a theoretical problem. In 2007, Amazon faced a massive scaling crisis and published their famous Dynamo paper. They declared that databases had to stay available 100% of the time, even if servers disconnected. But, but this threw the nightmare of resolving conflicting data directly onto the developers. Engineers were writing thousands of lines of fragile code just to figure out whose edits should survive. State tracking was an algorithm nightmare. Eventual consistency and CRDT. This brings us to a concept called eventual consistency. The system promises that if no new updates are made, eventually all replicas will converge to the same exact state. But how do they converge? If two people edit the same data at the exact same time locally, how does the system merge them later without a central authority deciding who wins? Across Europe, a group of researchers led by Mark Shapiro and Nuno Breguica realized the industry was looking at the problem backward. Instead of trying to build smarter servers to fix the messy network, they asked, what if we change the fundamental geometry of the data itself? They looked toward abstract algebra. They realized that if data structures obeyed a specific set of mathematical properties, like commutativity, where the order of operations doesn't matter, conflicts would become physically impossible. In 2011, they published a landmark paper formalizing this blueprint, officially coining the term conflict-free replicated data type. In essence, CRDT is a smarter, more reliant way to manage data across a distributed world. But to truly appreciate the genius of CRDTs, you have to understand the nightmare it was built to resolve. I will now hand over the floor to Rohani to show you exactly what happens when concurrent editing goes wrong and why older solutions just weren't good enough.
In this part of our presentation, we'll be learning about how CRDT evolved into being, why it was needed. Let's say you and your friend wants to collaborate on a project remotely. It could be code, an Excel sheet, or a text document. This sounds simple, but under the hood, concurrent editing introduces massive complexity. Let's look at a classic array. We have a string RO sitting at indices 0 and 1. You want to type P at the beginning, index 0, to make the word pro. At the same time, your friend types B at index 0 to make it bro. If the system processes your request first, the string becomes pro, then it applies your friend's request to insert B at index 0. The final result? BPRO. Neither of you got what you wanted. It will get even worse. What if you decide to delete the character O at index 1? At the exact same time, your friend wants to append the character S at the end of the string, which would be at index 2. If your deletion happens a millisecond faster, the string shrinks to just R. Now your friend's request to modify the index 2 will arrive, but index 2 no longer exists because you deleted that index. The system falls out of logic, conflicts will arise, and the application will crash. So how do we handle these collisions? The first generation of developers encountered this and came up with pessimistic locking. This is actually locking your document when you start editing for everyone else. This actually doesn't hold the spirit of real-time collaboration, and in reality it is vastly inefficient and out of practice. Later in 2000s, a better solution emerged: operational transformation, or OT. A central server is placed between the users. The server intercepts every request, mathematically transforms the indices so they stay logical, and syncs everyone up. This was a massive leap forward, but it introduced a new dependency. While OT does allow offline editing, it requires that central server to resolve the edits once you reconnect. If the offline divergence is too massive, the server struggles to merge them, causing bottlenecks or forcing manual conflict resolution. If you think about the internet community and users, it's actually massive. So handling everything with a central server is not actually a feasible solution, and the servers need maintenance. For that, when the server is disconnected, the conflict resolution and everything will fall apart, which is actually much problematic than it actually seems. This limitation is exactly why the industry needed a paradigm shift. In 2011, a team of researchers led by Mark Shapiro and Nuno Preguiça realized the problem wasn't the network, it was the geometry of the data itself. They looked toward abstract algebra to find solution. They discovered that if data structures obeyed a specific set of mathematical rules, forming what is called a joint semilattice, conflicts become mathematically impossible. The operations to achieve this must follow three strict rules: commutativity, the order of operations cannot matter; associativity, grouping cannot matter in case there are more than or three operations; idempotency, applying the same operation multiple of times must yield the same result. Because of this math, a CRDT gives every character its unique mathematical identity rather than an absolute index. Depending on the system, this is done through either state-based CRDTs called CVRDTs or operation-based CRDTs called CMRDTs. But in computer science, nothing comes free. There are always trade-offs. While the math is elegant, CRDTs come with three major disadvantages that the developers must manage. First is memory bloat. When you delete a character in CRDT, it doesn't actually erase it from memory right away. It just flags it as deleted, leaving behind a tombstone so operations from other offline users don't break. This causes massive metadata overhead, requiring complex garbage collection algorithms to stop the application from running out of memory. Second is implementation complexity. Building a CRDT for a simple counter is easy, but applying this math to complex tree structures like moving a folder inside another folder is notoriously difficult and prone to infinite loops. Third is the UX paradox. Sometimes the math works perfectly, but the human result is terrible. Building an undo button in a distributed CRDT is a nightmare. Think about it. When you click undo, do we delete your local action or do we delete the document's global action? Furthermore, if two offline users write a sentence in the exact same paragraph, the CRDT will flawlessly execute, interleaving the characters based on timestamp, and the math will succeed, but the resulting text will be unreadable gibberish. You are essentially trading storage, complex development, and edge case UI issues for a seamless serverless sync experience.
Thank you, Rohani. We now understand the problem deeply. Indexes crash, locking kills collaboration, and OT depends on a central server. What I'm going to show you is why the math makes all of that impossible to happen in a CRDT, not just what the rules are, but why they logically guarantee convergence. Rohani mentioned three words: commutative, associative, idempotent. A data structure that obeys all three forms what mathematicians call a join semilattice. The symbol U is the merge operation. Think of it as a special kind of addition that always produces a single correct answer. These three laws are not engineering choices, they are mathematical axioms, and from them everything else follows. Let's make this concrete. Meet the G counter, the simplest possible CRDT. Each replica owns one slot in a shared vector. Replica A owns slot 1, replica B owns slot 2. They go offline, they each increment independently. Now they reconnect. How do they merge? Merge is component wise maximum, slot by slot. Take the larger number. Both replicas commute this independently and arrive at the exact same answer. No server, no negotiation, no conflict. Now here is the core geometric insight. We define relationship between states called a partial order. We say state A is less than or equal to state B. Return A less than or equal to B using the merge operation itself. The V. Here the slash less than or equal to means A is behind B. We substitute regroup using associativity, then collapse the duplicate using idempotency. The result is S prime, which is exactly the definition of S below S prime, or S is behind S prime. This proves states are monotone. They only ever advance in the partial order. A replica can never unlearn information. Lemma 2 is the most important geometric fact. The merge result A union B is not just some upper bound above both A and B, it is the smallest possible upper bound. This means no information is invented and none is thrown away. We prove it in three parts. Part 1. The merge result is above A. We use associativity to regroup, then idempotency to collapse. Done. Part 2. The merge result above B as well. This time we use commutativity first to bring B to the front. then associativity, then idempotency. Part 3 is the key. We take an arbitrary upper bound C and prove that A union B sits below it. We regroup with associativity, then substitute our two assumptions one by one. The result is C itself, which means A union B or A merge B is behind C, since C was an upper bound. The merge is always the smallest possible one. Now we assemble everything into the main theorem. Suppose n replicas each receive the same set of updates but in completely different orders. Because the network is unpredictable, do they all converge? The proof is elegant. Any ordering can be transformed into any other ordering by swapping adjacent elements. Like bubble sort, each such swap is valid because of commutativity. Regrouping is valid because of associativity, so every possible ordering of the same updates produces the identical final state. This is called strong eventual consistency, and it is not a design goal or an engineering based effort. It is mathematical theorem. So here is the complete chain. A joint semi-lattice gives us monotone updates and a least upper bound merge. Those two lemmas together prove that any permutation of updates leads to the same final state. Conflict-free convergence is not magic. It is the inevitable consequences of the algebra. With that mathematical foundation established, I'll handle it over to Noor, who will show you how this becomes an actual code. Thank you.
Hi there, I'm Noor and I'm going to explain CRDT in action. There are many implementations and variants of CRDT, so I have chosen Loro CRDT because it is relatively modern and it is easy to explain. Let's take a look at Loro CRDT in high level. Here we have a function called sync that applies a bunch of operation on our state. At first, we topologically sort the operation to ensure that the dependencies of each of the operation is fulfilled before the operation is applied. After sorting the operations, we go through each of the operation, ensure that they are duplicate, and then we apply them on our state. Let's take a look at an animation for to be more clear. On the left side, we have a function, and the right side, we have a bunch of network ops, which we are topologically sorting. After topological sorting, we are going to apply each of them one by one in our local document. Here, we are applying the first operation, which says add A after C, and we have updated our document. In similar fashion, we are adding S after T, and our document becomes cats. Our final operation is delete the character C, and after deletion, our synchronization is complete. Now let's take a look at the topological sort function in Loro CRDT. The topological sort function ensures that whenever we apply an operation, all the other operation it depends on are applied already. For example, let's say we apply an operation where it says to delete the character C, and then we have two other operations which says add character D after A and then add character C after D. And if we apply the delete operation first, it's going to be an invalid operation because C does not exist in the document yet. So we have to sort it in such a way that let's say we put the operation add D after A as our first operation, and then add C after D as our second operation, and then we can delete C. And this is what this function ensures. And this can also be said as maintaining a proper causality. Here, I'm going to show you an animation that makes it a bit more clear. We have two things, a ready queue and a sorted queue. And we also have a bunch of operations. The weight level on the operation means which of the operations it is, or it indicates the number of operations the current operation is waiting on. For example, let's say operation 2. How would we resolve that? Well, operation 2 is waiting for operation 1 to finish. So the wait counter is going to be 1. Same goes for operation 3, which we can see it in action. Here we loop over each of the operation, check dependencies and increase the counters. And we push all of the operations that are immediately ready for our sorting. We go through each of the operation, we push it to sorted queue and go through the pending operations. And if our current operation that we have just pushed into sorted queue is a dependency of the pending operation, we reduce the pending operations counter because we have just applied the operation. And here, let's say operation 2 is dependent on operation 1, so we are going to decrement the counter to 0. And now as operation 2 has counter 0, so it's going to be pushed to ready queue, and in our next iteration operation 2 is going to be pushed to the sorted queue. Similarly, we resolve operation 3 and sort it in such a way that operation 3 comes after operation 2. And now our sorted queue has been calculated and our causal sorting is complete. Now let's take a look at insertion in Loro CRDT. When we are inserting an operation in our CRDT state, we have to ensure two things. First, we have to resolve concurrency, and second, to resolve the concurrency, we follow a bunch of rules. First rule is whenever two operations are concurrent, the operation with the latest timestamp wins first. If both of them have the same timestamp, then we have a PRID to compare against. If an operation's PRID is greater than the other operation's PRID, then the operation with a higher PRID wins. This mathematically ensures that a conflict is always resolved. Let's take a look at an animation for more clearance. Here we have an active document state where we have C, A, and T in the document. Bob's O arrived first with timestamp 10 and PRB. Meanwhile, Alice's operation, which adds H on the right side of C, arrived second with timestamp 10 and PRA. After inserting Bob's operation, we can see that the letter O has been in the active document state and the document spells COAT. We now find the left neighbor of Alice's operation, which is C, and we find the position of that neighbor. And then we add 1 to get the next position where we are supposed to insert our operation. So we do that and then we loop until we find a valid position to push our operation. Here, the first operation is O and it is concurrent with our current operation H because both of them share the same index. So we have to do a tie-breaking algorithm. And in this case, we first compare the timestamp. But here's the issue. The timestamps are equal, so we have to compare them by PRID. And PRID of A is less than PRID of B. So Alice loses. In this case, we move on to the next index and check for concurrency. Here, they are not concurrent because they don't share the same left node or operation. So we insert H because it wins against A. And our insert operation is done. Let's take a look at deletion in Loro. Loro deletion is more of a visual thing than an actual state altering thing, because when you delete a character in Loro CRDT, the character is marked as deleted, but it is never actually deleted. This ensures that we can go back in time anytime we want, and when two operations come at different times, let's say we say user A deletes the character C and user B adds a character D after C. Now when user B was doing that, he saw the letter C, but user A, when deleting that, he did not see the letter added by B. So in this case, if we deleted C immediately, the insert function would fail because it would not be able to find C. So in this case, when inserting D after C, in case of user B's operation, we find C in the document, but it is marked as deleted. So we just add it beside C. In this case, memory is not saved, but it ensures that our hierarchy is proper and we don't try to add to any non-existing value. Let's take a look at an example so that we can learn how deletion works in Loro. Here we have two different representations. One is the internal engine, the DAG, and the user interface. Let's say we want to delete the character A, so we choose the character A and then mark it as deleted, which can also be said as tombstoning. After it is tombstoned, we find the index in the visible part and then we just remove it from the user's interface. Here the user no longer sees the character A, but in actuality in the internal database engine we see that it is there and waiting for other operations that are dependent on it. So it actually remains in history. So that was about how Loro CRDT works in detail, and I'm going to hand over to Shahriar, who will explain the real life usage of CRDT and how it solves practical issues.
Thank you, Noor. At the very beginning of our presentation, Irfan mentioned tools like Notion and Figma. Now that we have seen the pseudocode, I am going to show you how those mathematical concepts power the apps we use every day. Okay, let's start with Notion. What Notion does is that it breaks every document into blocks, a page, a paragraph, even a checkbox, all into blocks. Think of them like sticky notes on a wall. Each one has a unique ID and a small counter that ticks up every time someone touches it. Every edit boils down to one of the three things: add, change, or delete. Adding is straightforward. When two people add something to the same spot at the same time, both survives. The system picks an order automatically. Then for changing, every edit carries a timestamp. For the same field at the same time, the system checks the timestamp. While this last writer wins approach is simple, it can be risky due to system clock drift. But for basic text blocks, it usually suffices. And for deletions, Notion uses the exact same tombstone method Ruhani explained earlier. It doesn't actually delete the block, rather it just hides it so that incoming offline edits don't crash the system. Suppose Alex changes a page title to meeting notes, but Ben changes it to meeting agenda at the exact same time. They synchronize. The system sees Ben's timestamps was a millisecond later and Ben's title wins. Meanwhile, Alex goes offline and adds a new text block. Notion just assigns it a unique ID. When Alex reconnects, that block drops perfectly into the document alongside Ben's edit. No warnings, no lost work. Now, let us talk about Excalibur, a free open source virtual collaborative whiteboard. Where we are drawing boxes and arrows, our teammate is doing the same thing at the same time without any kind of problems. Well, everything on the canvas is an element. Each one has a unique ID which has a version number. When changes arrive from another user, Excalibur runs what it calls a reconcile. It looks like that every element compares version numbers and keeps the higher one. A quick example, suppose Alice is resizing a box, but Bob is changing its color at the same time. Their changes synchronize. Alice's resize wins on version number. Bob's color change is on a different property, so it just applies. The CRDT merges the properties. The box gets Alice's new size and Bob's new color. But what if two people edit the exact same shape at the exact same time? Same version number, same property? Well, let us remember the massive system crash Ruhani explained earlier. Excalibur avoids that by giving every edit a random number. If two users changes a box to different colors at the same time, their version numbers die. Both devices simply pick the lowest random number, guaranteeing they both agree on the final color without the server deciding. Well, to summarize, what do Notion and Excalibur have in common? In both apps, the server is just a dumb messenger passing encrypted updates. The actual conflict resolution, the math Pranthik and Noor showed us, lives entirely on the local device. As Ruhani mentioned, this does come with a trade-off. Those hidden tombstones pile up in memory, but the payoff is that neither of these apps ask us to wait. Neither interrupts us with a conflict dialogue. They just work quietly and invisibly. And that is the real beauty of CRDTs. With this, our presentation comes to an end. We hope our presentation has provided meaningful insight into the fascinating world of CRDTs and demonstrated how these powerful concepts quietly enable the seamless real-time collaboration experiences that shape modern digital life. Now, I would like to conclude our presentation here. Jazakallahu khairan.